Thank you, SAP and Docker Meetup for having me here. I'll be presenting demystifying container primitives and runtimes. You have seen a high-level talks on like Docker securities and Kubernetes. This particular talk is more about like a prequel to them, like how does actually container works? What are the things in the OS which makes containers to run, or which makes container possible? Okay. So yeah, my name is Rohan. I work as in DevOps and in AWS. So I started as in teaching and system admin, then Amazon's data center, and now as in DevOps. Okay, I'm not representing Amazon. So yeah, so outline for today. So yeah, today's outline is like we'll see like what are actually containers, how do we define containers, and what are the primitives, what are the building blocks which makes container, and what are the different runtimes which are available today, and the Firecracker. So yeah, so what are containers? So first to gauge the understanding, like I would like to know like how many of you are just the beginners for Docker, okay, intermediate and advanced, okay. So I have like a lot of stuff for both categories. Okay. So yeah. So if we say like if I ask like what are containers? So what are how will you define it? Like is it VM? No. Does it look like VM? Yeah. At the high level, we can have shell in it, just like VMs. But it feels like VM because it has own process, network, and we can have own packages and those things. So one more thing, like how many of you used like chroot? Like chroot is a program of Linux which was like a very early implementation of containers. So you can consider containers as like chroot or maybe advanced chroot. So it gives you a process isolation. What containers are not, they don't have their own kernel. They can't boot up their own OS. They can't have their own PID, and it's just a collection of processes in which we isolate. Okay, so this is a basic difference. On the left, I have a VM which has hypervisor, individual guest OS, binaries, and applications. On the right, I have a Docker engine which has just libraries and the application. So again, what are containers? So it's a collection of it's a like containers are abstraction over the several Linux technologies, which are basically uh, like the CPU, memory, disk, and those kind of things. Like how do we isolate and group them together to make a different process running? So container has been there from a lot of time, and in last 3-4 years, it has got a like good surge in adoption, and and one of the major implementation of containers is Docker, because Docker has come up with easy to use tools which has made containers easy for the masses to run things. So yep. So in short, there are like four atomic functions Docker, like to build the image, to push the image, to pull the image, and to run the container, right? So this is how the things work. We have a Docker file, we write a Docker file, we build it, we push it to Docker registry, then we pull it and then we run it, right? So these are the basic components. So every Docker has two components: the Docker installation, which one is client, and the Docker daemon, which is Docker host, or the you can consider as a Docker service. And there's a third service which is registry, which could be a Docker hub or any private registry. Okay, so yeah. So as we see, like uh, when we have a Docker file, we build it. This is a kind of image we get. Image is a single file which contains all the dependencies, all the configuration which are required to run that particular application. So it has its own boot FS. It has own kind of base image and the instructions which you add over it. Now when we hit a when we start a container, we use a command docker run, and we just give an image name. So what does happen at that time? So as I said, like that two components of Docker. So The Docker run, when we run a Docker, it passes the Docker client passes the command to Docker server, and then Docker server has its image cache. So it checks whether the image is available over there or not. If it's available, it runs from there. If not, it pulls from the registry and it starts the container. So a running container is nothing but a kind of instance, running instance of an image. Okay, so Docker has two parts, client and daemon. Docker client does not actually do anything. The main part is done by the Docker daemon, which is Docker server. Okay, so Docker server is actually responsible for creating images, maintaining containers, uploading images, doing everything which is possible today by Docker. Okay, so uh, so like we have discussed like how does things work and those things. So you might have a doubt or have a question like how does this things works. So how many of you have like tried opening the kernel code for Linux, kernel.org, and like, so have you tried grabbing out containers, LXC, or those things? So if you try to do a grab of containers, you'll not find anything, or if you find anything, it won't be relevant to Dockers, because container itself is not a capability of kernel. So the capability of kernel which is used to run containers is cgroups and namespaces. So in this next section, we'll discuss what are cgroups, what are the namespaces, and related things. Okay. Yeah. So building blocks. So this is how Linux kernel looks today, or the complete OS. You have number of applications like Chrome, Terminal, and number of things. And kernel is a intermediate function uh, which talks to the hardware, and the application talks to kernel. So this is how Linux system works today. Okay. So most of the Linux systems have their own kernel, and yeah. So when we say namespace and C group, so namespace is nothing but a kind of isolation. It provides isolation like this particular section of hard drive, this particular section of network, or this particular set of users are are belonging to this particular process, right? And the C groups is a kind of metering and limiting factor. So it limits like how much memory your container can use, how much CPU it can use, and those things. If even if you don't set the limit, it can you can use C groups to account for the memory and other resources. Okay, so how does these two things fit together? Let's see an example. Suppose you have two applications. Both of them have a requirement that they should have two different Python versions. So in a particular system, without using environment in Python, you can't have two versions of Python running, right? So with the help of containers, you can have this thing. So the dotted line is a container boundary. And let's further zoom out. So this is the view which container sees. When we run a container, it sees like it has this application kernel and those resources over there. Yep. So now let's further do a deep dive on like what are control groups in depth. Okay. So yeah, as I've given a document link over here. So if you want to read about like what are the actual implementation of C groups, what are the functions, you can read over there. Uh, okay. So what do C groups do? They organize all the process in the system. They limit or prioritize resource utilization. They account for resources. Okay, so the C group itself is an abstraction framework. However, the subsystems, which you can see memory, CPU, and network, these are the actual concrete implementations. Okay, and within a C group, there are like number of subsystems. So subsystems is what are the resources which you want to control or account using C group. Okay, so it could be memory, CPU, the disk IOs, the discrete process IDs, the actually what is the container is, CPU, memory pinning, freezing, and those things. So what I'll do is I'll discuss the major subsystems which comes into the play. Okay, so yeah, some basics. Like every C group has its own hierarchy. This means CPU has its own hierarchy, memory has its own hierarchy, and I'll show you how. So this is the location sys fs group. So when you run a container, and if you go to the this particular location, if you do ls, you'll see these are the subsystems which you can see on the system. Okay. So for the Ubuntu based systems, it is typically mounted over sysfs cgroup. For the Amazon Linux, Red Hat, CentOS kind of system, you'll find it under the slash cgroup option. Okay, so and yeah, so whatever container you run or whatever process you run, if you run with a C group, you'll find that particular process inside one of the subsystem, whatever you've used. Okay, and I'll in the demonstration part I'll show you how. So yeah, so the memory C group. So this is most important C group. So you can have like memory C groups gives you option to enforce some kind of limits. So it could be soft limits and hard limits. So if you remember, while running a Docker run using command, we give memory and the memory reservation, right? So memory is the hard limit and memory reservation is the soft limit. So those things comes from the C group. C groups gives the capability of giving the soft limit and hard limit. And if you define the soft limit, you may know like it allows container to use whatever is resource available, but it helps in like reclaiming the memory when the system is under the contention. And the hard limit is the one beyond which your application cannot use any memory, and if it tries to use, you'll give out of memory. Okay, so you might be knowing that two kind of triggers for OOM. One is at the kernel level, which is started or which is triggered by kernel, and one is at the C group level. So the one which is at the C group level is for a particular container or particular process, and one which is at the kernel level is could be for like any process which is running on the OS. So it is always recommended to use the hard limit at the container level because it won't disturb the complete Docker system itself. Okay, so the next C group is the CPU C group. So CPU C groups helps in keeping the track, like how much CPU time or how much threads or processes are used by that particular process. Okay, so you can set weights, but if you see, we can't set the CPU limits. You can set the weights kind of thing, like this process can use this much CPU and this one, but you can't limit it directly. So the next important C group is device C group. So it gives the control over like what are the different devices on the underlying system can be used by the container. So one of them is the random and the null, which is used for generating entropy, or it could be the GPU nodes and those devices. So you might be knowing like under slash dev we have all the devices, right? You have all the disk, you have all the devices, USB printers and those things. So this is the particular C group which allows us to share the underlying devices with the container. So the next part is namespaces. So as we have seen in the intro part, the namespace is used for isolation, right? So it provides the isolation mechanism. It changes. Uh, uh, it like the C group is for limiting how much resource process can use, and namespace is limiting what what are the resources which a process can see. And it just like C groups, namespace also has some kind of subsystems, and we'll see how. So these are the available namespaces: network, file system, process ID, inter-process communication. So for an example, what does network namespace do? So when we start a container, when we start a container, it gives a connection to container to the your ETH0 or bridge. So the network namespace is the one which helps in connecting or wiring that particular container to the actual network. So file system is when you mount something to your container. The process ID is like every container is a individual process, and when you exec into the container, you see the container cannot see the other process. Or when you do PS from your system itself, from the Docker host, you see all the process over there. So the namespace gives the isolation to that particular process, not to entire system. Okay, so the network namespace is very frequently used namespace in container. It provides a separate network for a particular container per container. Okay, so the best part of the network namespace is you can if you know like how does the namespace works. So even after creating the container, you can get inside that particular namespace and you can run random commands. Or the best part of network namespace is you can switch between the network namespace. Suppose you have two processes, and if you want to share the network namespace, this means the same ETH0 should be visible on both containers. You can make that possible using the network namespace. Okay, so it is widely used in pods and ECS service. In ECS, there's a network mode called AWS VPC where a particular container gets its own ENI. So network namespace is the function which comes into the picture. Okay, so the important part of network namespace is once we give the network namespace to a particular service, that a particular container gets its own network space. This means it will get its own IP routing table, IP tables, and sockets. Okay, so if you might have done Docker exec into the container, you will see ETH0 and a local IP 172 series, right? When you come out, you see some other IP on your system. So that happens because of network namespace. So other important namespace is PID namespace. PID is process identifier. So where does it comes into the picture? It comes into the picture in isolating the processes so that one process should not see other. So this is the very fundamental namespace which is used in running the containers. Okay. Another important namespace is MNT. So when you do mount a volume and those things, so this is the namespace which comes into the picture, which mounts or which shares the namespace with the actual mount and your container, so that only that container can see that storage. Other containers would not be able to do so. This is also important concept in namespace that uh, the namespaces can be shared across the processes. So process one, consider process one as in one container, B and C the four containers. So you can have a PID namespace shared between two containers, and you can similarly you can have network namespace shared between two containers, and the mount space shared between three containers. So this can be done via Docker client itself, or you can do it via command lines of Linux. Okay, so next part is runtimes. So what is container runtime? Runtime is nothing but a program written which helps in executing these namespaces and C groups. So when you say I want to start this particular container, runtime is the part of program which creates a namespace and C groups for that particular process and runs it. Okay, so once the container exits, the namespace and the C groups are destroyed. So the different examples of container runtimes are the Docker containerd CRIO, which is used in Kubernetes, RKT, and systemd spawn, which is like almost deprecated, but it's, right now it's there. So there's an organization called Open Container Initiatives (OCI), which is standardized. Like how if you like suppose if you want to develop your own runtime, so it gives the recommendations or set of instructions that these are the things which should be there in your runtime so that it would be working with other counterparts as well. Okay, so runC is the runtime which powers Docker. So whenever you get a time, when you do a Docker PS on your host system, try to grab runC. You'll see a special process over there, or you can check it on the command line as well. Okay, so as I said, like the OCI gives uh, the format, like how your runtime should look like. So this is what it gives. It gives like these are the number of parameters which your runtime should know or should be using. Okay, so every container is a bundle. So by bundle I mean it has a file system which has which has your base image and those things. And if you untar the image, so when we do a Docker pull, you can do a dump. After dump you get a tar file. If you untar it, you'll see there's a JSON document which defines what are the different layers which this container uses, and you'll see the same JSON file over there, which defines how this container is built, how it should be used. Okay. So these are the major runtimes available. So one of the important is containerd, and there are others as well. So LXD is a Linux containers which was used earlier, now not in use, and CRIO is the implementation done by Kubernetes teams. Firecracker is the runtime which is like out of AWS, and runC, which is like the base of everything. So this is how runtime looks. So when you issue a command at this place, when you issue a command like docker run, it goes to the Docker engine, then it goes to the containerd, then containerd starts a shim, and that shim starts a runC, and that runC starts this container. Okay. So next time when you run a container, when the container is running, try to do a PS over the container. You'll see, or let me show you. Is it visible? You see, like I have one container running. So if I do PS3, you'll see containerd, shim, and nginx. So the nginx, the containerd takes over the control moment the runC has completed its work. So the runtime would not, uh, runtime generally does not used to keep running all the time. It just executes the container and it quits, and it gives the control to containerd. Okay. So you'll see docker d, this is the daemon itself, this is the containerd, and these are the subprocesses, right? And let's see the cgroups as well. uh, so within memory, you'll see these are the number of subsystems within memory, these are the number of nodes within nodes. You'll see docker. So you'll see this only when the container is running. Moment I stop the container, this a particular node will be gone. So let's see what is inside the docker. Within inside the docker, you'll see this is uh, the container id of our container. So within this container id, you'll see these nodes, and from there we can see like what are the stats what is the memory which is being used. So let's try to see this. So you'll see these are the stats for this particular container with respect to memory, right? So when you do a Docker stats from the Docker CLI, this is the same thing which you get over there. So these are the building blocks. Yep. So this is how the complete the things are wired up. So these are individual components. This means uh, if you don't wish to use Docker, you can have containerd and runC installed in a system, and you can directly interact with that. okay? But you'll not get the same functionality which Docker gives you. Or if you don't like containerd, you can just have runC and you can start your containers. But runC will just execute the containers. It will not build the container for you. It will not push or pull the container. Okay. Yeah. So the Linux containers, these are the very primary kind of containers which came into the picture a long time back, even before even before the Docker and those things. So LXCs are still there. So if you want, you can install LXC and it will give you the similar functionality as LXC. Even when Docker started, the first version of Docker was based on LXC only. Later they started their own version called containerd and runC. Okay. So now the Docker engine. Docker engine, as we discussed, like it is a client server kind of model in it, and it talks using the REST APIs, and the Docker helps you in managing the container, the complete life cycle itself. Okay, the images, builds, execution, and those things. Okay, so these are the components of Docker: Docker API, Docker CLI, plugins, containerd, which is your runtime. Okay, and for building the Docker, this is the Docker building kit, networking, the different network plugins like the bridge and those things. Those functionality comes from here. These are the volumes, uh, volume plugins like the Rexray and the different volume plugins which you use. So those are the different components. It is a plugin based system. So apart from containerd, there's one more runtime called RKT, or we pronounce it as Rocket. So it is also a similar kind of implementation, but it is more application specific. So I haven't used Rocket directly, but one of the implementation I've seen is in Kubernetes, where like they were trying to use runtime as RKT. So one of the thing is uh, when you start a Docker, you have a functionality that suppose you don't want to use runC, you can have your other or some other runtime, and you can use Docker along with that, as long as it follows the OCI standards. Okay. So one of the example of that is Firecracker. So Firecracker is one of the container runtime which came out of AWS, and it is an open source. People used to contribute it. So what is different in Firecracker? Different in Firecracker is like for every container we launch a micro VM. This means at the very beginning we discussed the difference between VMs and containers, right? So the micro VMs gives the some of the functionality of VM, like the security of VM, to the containers. Okay, this means you can run a multi-tenant kind of workload on the same Docker host. Because today, if you have two customers and you're running a workload of two customers on the same host, you never know, they can see the process of each other, or they can exploit some vulnerability, right? So if you have the isolation of the VM level, this means this is completely secure. Okay, so in Firecracker, in runC, we used to provide the OS resources as a part of a kernel and directly map it to containers. But in Firecracker, we present them as in different devices. Different devices. This means it is supported by KVM. This means the disk, kernel, and the root FS, those are presented as in different devices altogether. And in Firecracker, we have removed everything which is like unnecessary. Only thing which you get in the micro VM is the display, keyboard, and the block devices and the CPU memory. That's it. So we have reduced the surface area. So the surface area is short. So there's no point, or there's a less possibility for attacks surface. Okay. So yeah, this was my part. So any questions for me? Yes.
Hi.
Yeah.
Okay, so I'm a cloud architect, and This question is more related to fundamental. So there are different scenarios, and you mentioned some runtimes and the engines. What is different criteria you use to choose certain runtime for certain application or certain? Let's say the fundamental question is sometimes you have to build something for a customer, and you want to start from OS. What OS you choose, what kind of runtime you choose, and how you deploy. So what are different criteria you think of when you?
So you can see this as like what kind of orchestrator you're using. Suppose if you're using Kubernetes, so in Kubernetes you'll not find the Docker client itself. You'll see the kubelet is directly interacting with containerd. And in other systems, like if you see ECS, this is a implementation of Amazon's orchestrator. You'll see there is a Docker client and Docker server itself. So it depends at what level you want the control, because every layer you add over the runtime, you add some functionality and you add some abstraction. So if you want to manage those things manually, you can have the lower layer. Suppose and one of the example I just showed is like if you are if the Docker host has just your workload or just workload from just your company, you'll not mind multiple containers running on the same host. But let's consider the point of view of cloud providers. If they want to have multiple containers on the same host, they may see like security as a major constraint, right? So that's why they'll select Firecracker. So it depends what are the things you want in your runtime. If you want more security, you can use Firecracker, and the many implementations like Firecracker itself, you can use that. Or if you want to just have the normal functioning, if it's your company, your infra, your on-prem, you can have runC. So those kind of stuffs.
Okay, thanks.
Yeah, I have one question.
Yeah.
I develop one application. I build that application and I create the image. And when I run that image, then how to define how much memory, how much space? As you told, this is the daemon thread, like Java in the daemon thread, that running in the thread. So how to define? Okay, I am the architect. I have 100 service, so how I define, okay, this much memory or space required to run my this container. So how to define in the higher management also, or any other team
Okay,
also?
you mean like how would you decide like how much memory or CPU you should
Yeah,
use?
yeah.
So generally what we do is we benchmark the applications. We start with like suppose 1 GB, 1 CPU. Then we put our load on it and see like what is the benchmark results. So if it is going around 100% all the time, we'll consider increasing it. So there's no you can't say there's just one number which will fit for all. It comes over the time.
Okay, I have some 100 customer is there, one application.
Mhm.
It at a time 1 hour, 100 customer. So how to define? Okay, I cannot do like manually. You can test 1 hour. Okay, how much memory will take? Then after 1 hour, I can take how much memory. I can benchmark that way, or I can directly how to identify. Okay, this is the memory will require 100 customer, 100 transaction is happening. So how to identify?
I think if you're running a multi-tenant kind of workload,
Okay.
as you're saying, so what you can do is you can start with a basic number, or let's consider an example of, let's forget the container. How do you start a VM today? You start with some default numbers, right?
Yes. Yes.
When you see the utilization is going 100% over the time, then you consider increasing it. Otherwise, it's just 10, 20%. You have to decrease it.
Okay, okay. And another one question.
Yeah.
Suppose I have two application, two container is there.
Mhm.
And suppose one container is communicate another container because I need some fetch some data. So in between that is the another container is down. So in between that is the some down is happening. So how to keep that transaction? Suppose I am sending some request. One container is going to another container. In between that is the some down second container. So
Okay.
how to maintain that data? How to capture data? Where I have to put that data?
See,
Data.
as you said, like you have multi customer approach. What you can do is you can have multiple bridges or custom defined networks. So if your one customer is on one particular bridge, this means they'll share a one broader network namespace.
Okay.
This means other containers or other customers which are running inside, they won't be able to sniff the network over here.
No, what my question, one container is depend to another container, because suppose when I search one flight, that flight means that is the search functionality, another functionality is there. I fetch some data, some other container.
Okay.
So when I'm fetching the data, that time some second container is down. So customer don't wait for that moment. So that data where will that million of second that data also loss.
Yeah.
So how to maintain here?
I don't think in terms of network there's a solution for that, but if this is something like you have some logs and you have some sidecar which collects the log, what you can do is if your data is so critical and like the second container can go down, I would prefer to dump that data over the volume and then pass it over.
Okay.
So that you have a buffer, even the container goes down, you have something where you can pick up.
Okay, thanks.
There. Yeah.
Take up the last question.
So I just wanted to know how multi-tenancy can be achieved through Firecracker. So Firecracker, I think it's mainly for the security purpose, wherein you impose additional security on the container. But how does it can help in achieving the
It helps
multi-tenancy?
it gives you a VM kind of boundary. When you launch a VM on VMware, this means it has its everything of every device of its own. Yeah. This means the one VM cannot see other, or if it's EC2 instance, one EC2 instance can be on the different same host, but you cannot see the data of others. So the Firecracker it uses the virtualization approach of KVM. So it literally gives you a micro VM. This means it has the complete isolation, which you see for the VM. So it's not just from the security perspective, it's also from the performance perspective as well. Because if you start a VM, it has the full-fledged OS, right? That OS has number of modules, number of things. In Firecracker, it's just a stripped down kernel. This means it has just a few very stripped kernel and few drivers.
Okay, how does it different from the CH root?
Pardon?
How does it different from the CH root?
Yep. In CH root, you just get a jail for a particular process, right? But the difference between it has the same difference which is between the containers and CH root. For the containers, you get a complete network stack, a storage stack, and those things. For Firecracker, again, you get the same things.